a really well-behaved crowd, and it's actually cool to see such a turnout, kind of almost filling the room. That's impressive. I'm Trevor Darrell. I'm a faculty member here. I help co-organize BEAR, and I'm really fortunate to be advising some of the awesome students who are leading the BEAR Climate Initiative. And so I'm here to help kick it off. And today we're basically trying to launch this initiative, which is going to build connections around AI, climate, and other topics across the Berkeley campus. And so we're really excited about that. And we're really fortunate to have Jennifer Chase here helping us kick this off. So I'm going to hand the microphone over to her to welcome you all. And then we'll turn it over to Ritwik and Colorado, who will present kind of the overview of the thing.
Okay, thank you, Trevor. And thank you for letting me be a part of this. And really, it was done entirely by others. But I'm really excited about it. I am the Associate Provost of Computing, Data Science, and Society. So for many of you, I'm your dean. Really, one of the most important pieces of computing, data science, and society is bringing together all the different people who are doing things around climate and sustainability in a data-driven way. So partnering with David Ackerley, who is there, who is the Dean of RCNR, the College of Natural Resources, partnering with people in chemistry like Ron Cohen, who is sitting there on his phone. And really, you know, I had heard, I don't remember who it was from, but somebody said that 1/4 of the faculty on this campus are either working on something related to climate and sustainability or want to. Maybe that originally came from Ron. Oh, sorry, I'm not. You can't see me. The camera is right there. Hi. Anyway, so yes. So, you know, one of the things I'm doing is I'm working with David Ackerley and with others across campus to try to bring some of these efforts together. We already have funding from Schmidt Futures for $12.5 million institute for data science for the environment, which is joint between our two colleges, or we're a college to be. We're hopefully less than a year away from being a college. And I was just really excited by all the topics here. And I think one of the questions is, how do we weave all this together? Before I came here, I talked to Dan Kamen, who is a faculty member. I don't see him here, but you know, he said to me that sometimes it seems that the whole is less than the sum of the parts in climate and sustainability because there's so much going on here. And so people like me and David Ackerley and others are here to try to make the whole greater than the sum of the parts. And thank you so much for letting me be a part of this.
Excellent, thank you very much. And so we'll hand it over to Ritwik, who will introduce the BEAR Climate Initiative and MC the rest of the event.
You can hear me? Right? Okay, cool. Thank you, Jennifer, for the aspirational words. I think that's really all we're trying to do here is make more of the parts and make sure that as a community we can give back and make sure that we're having real impact for the world. And so again, thank you all for being here. I know some of you have traveled far to actually be physically present. And we're really excited to share with you the Berkeley AI Research Climate Initiative. So my name is Ritik Gupta. I'm one of Trevor's PhD students, and together with Colorado Reed, who was on Zoom and no longer is, and Medani Narasimhan, who's somewhere in the room here, we've been basically brewing this for the last 1.5 years to basically find ways to unite our communities together to do more meaningful work in the space of climate change. So back in 2012, one of Colorado's old mentors, Kiri Wagstaff, a NASA JPL scientist, had this quote in ICML that much of current machine learning research has lost its connection to problems of import to the larger world of science and society. And that rings true today, right? I mean, we as AI researchers sit down today, and I think some of the most common conversations we have is, why are we doing this? Why do we do reinforcement learning? Like, all of these conversations I hear throughout this last week, even today. And I think the thing to focus on is these problems of import, right? What do we define as problems of import? What are the things that actually matter, and why are we doing what we're doing? And answering that question of what matters is really difficult. And so instead of coming up with the answer ourselves, what do other people think about it? If we go out and we ask random people on the street, which is what UNESCO did back in 2020, they surveyed 15,000 people and they asked them, what is the most pressing problem of our time? And 2/3 of them said climate change. Okay, that's one answer. Let's ask our president what he thinks the #1 problem facing humanity is right now. And his answer is climate change. And so from the bottom to the top, we all agree that climate change is the biggest problem facing society today. And the thing is that as AI practitioners, researchers, and engineers, there's a lot we can do to actually help climate change. We can help prevent it. We can help create better materials. For example, what for photovoltaics that can help prevent climate change by better materials creation. We can help understand it, and we can help adapt to it. And so, there's a wide variety of applications. I'm not going to bore you to death by getting into every single one of them. You can go to any of these websites, Climate Change AI or HADR.ai, to see different examples. And so we all understand that we can do something to help climate change. We have seen the power of AI in all sorts of other domains, yet it's a hugely marginalized topic in active AI research. Colorado and I, we dug in. We went to Google Scholar and we said, okay, well, how many of our major conferences are there any papers that actually mention climate or disasters? And you can see this is a log scale. And in the last decade, barely any papers even mention the word climate or disaster, let alone focus solely on them. And so we all recognize that climate change is a huge problem from the bottom to the top. As AI practitioners, we are fully aware of the fact that our research can actually help climate change in some way, shape, or form. So why aren't we doing more about it? And so here's the thing, right? We live in this little island of core AI contribution. We're sitting here with our toy data sets and benchmarks. We're publishing new and new, better and better models, larger and larger models. And then what happens is someone comes along and says, hey, that's cool. Let me go apply that to some meaningful problem over in this other island, across the world. And this one person or two people or three people take this contribution from the world of AI and they translate it and apply it directly over to this other meaningful problem. It's a very one-way process, right? It's very application oriented. And so, yeah, this is this application process, preempting my slides. But here's the thing, right? This other island is a completely rich field in itself. And it's an entire source of real world problems that can actually be used to drive core AI contributions. For example, the world of climate is super messy. It's constantly changing. It's always evolving, and we don't really fully understand it. And in order to actually fully tackle these problems and apply solutions to it, we actually have to come up with core AI contributions to even understand or model these different sorts of issues. So by looking at this thing as a bridge, right? But by bridging these two communities together, these two different islands together, we can do more meaningful research that has an impact on the world. And so the thing is, all right, we can build this bridge. We can do interdisciplinary research all day. And I think we can call that bridge CDSS. Exactly. We can build these bridges. But the one thing that we really lack is a common language, right? We met Dan a couple months ago now, and we started talking to each other, and he's talking to us about snow water equivalents and all sorts of different things. And we're talking to him about optimization and vision transformers. We're just talking past each other. So how do we, we build this bridge, we build the infrastructure, but how do we learn a common language to actually do this meaningful research? And our hypothesis at the Bear Climate Initiative is that benchmarks and data sets can serve as that language. As it turns out, in both of our fields, climate change and AI, we use a lot of benchmarks and we use a lot of data sets. In AI, we have ImageNet and COPA and all sorts of other things. They're very standardized. Every single time we write a paper, we always have to show results on the same exact benchmarks. And in climate change, it's a similar thing where every single person is collecting data. They publish the results on that data. They come up with new ways to analyze this data. They share those results. But again, we all are using data. So if we can come up with more meaningful benchmarks and data sets that help us contribute better AI research and better climate change research, then we actually remove a lot of the barriers to entry for either person to do interdisciplinary research. And by bringing these group of people together, they start creating better data sets and benchmarks, to start doing more meaningful research. And not only do this research, they do it iteratively, right? We don't just make one data set that's like, we publish it once and it's forgotten forever. We work on updating it forever. The climate is changing, these data sets need to change with respect to the climate as well. So how do we work towards a data set process rather than just making bespoke data sets and benchmarks? That's really what the BCI is aiming to do. And so that's really where we get into the meat of the BCI, right? Our goal is to unite AI and climate-related research to solve difficult scientific problems that necessitate bridging our communities together. It's not just an application thing. It's in order to actually do AI research that matters, like things that are going to be best paper at CVPR and also best paper at Nature. We need to bring our communities together. We need to learn to talk to each other, and we need to find ways to collaborate, even though collaboration seems harder and harder in today's world. And by doing this, we want, and in order to do this, not just in doing this, in order to do this, we need to maintain this bridge, right? We've built this bridge, we've built CDSS, but we need to keep making sure that we invest more and more time and resources into making sure this bridge doesn't collapse. And our nation does have an infrastructure problem anyways. And we aim to do this by bringing together people from all across Berkeley, right? Climate researchers, people from ESPM, College of Natural Resources, LBNL, everyone, all of BEAR, researchers and students to work on these meaningful problems and benchmarks. We have, this is a brief list of all the people involved right now. I think this list is actually even out of date. If you go on the webpage right now, there should be like 10 more people on this list. Let's work on some of these problems. So that's the goal, right? Let's work on some of these problems. Let's put out a data set process that helps us build better benchmarks and data sets that unites our fields together. And that's really the goal behind BCI. Now I'll hand it over to Colorado to talk about a particular instantiation of how we're doing this, a project called The Fate of Snow that we've been working on together with Meta and LBNL and other partners. But I won't steal his thunder too much. I'll let him share what The Fate of Snow is.
Wonderful. So thanks so much, Rithwik. And can everybody see my floating head there in the audience? If not, if you can hear my voice, you guys are good. Okay, wonderful. So Rithwik gave a great high-level overview of what we want to do with the BCI, right? Bridging the AI core AI research contributions with meaningful climate-related problems in such a way that these problems couldn't necessarily be addressed without developing some new core AI research methodology and ideas. And that's what we're really excited about. And we go and we spoke with a lot of different folks in a lot of different departments at Berkeley and our industrial collaborators and so forth, and discuss the types of problems they were working on. And one that really stood out to us was this, what we now call the Fate of Snow. And so the Fate of Snow is a collaboration, first and foremost, a collaboration with a diverse group of experts. And so this is around half the folks involved with the Fate of Snow. And you can see there's some borders along each person, their profile image here. And the blue ones are folks that are working here in BEAR, in EECS, and the ones with the green borders are working in a climate-related field, hydrology and atmospheric science and so forth, right? So right from the start, we're bringing together different experts, different researchers and different backgrounds, as well as some wonderful industrial partners. These are the people at the table in the little clip art image from before. And okay, so what's the project about? The Fate of Snow, and as I've learned, snow melt and snow water is incredibly important. So around 1.2 billion people directly rely on snow melt. And it's not mostly just for showers or drinking water. It turns out most of the water goes to agriculture and power. But on a climate side, in addition to looking at our use of water and our reliance on water, everyone benefits from the cooling services provided by snow because, well, snow's cold, right? Also, it insulates the ground. It keeps water that's in the ground over the winter months as the snow provides a nice insulating layer. So it's this incredibly important resource. And there's this difficult long-standing problem for water resource managers and the hydrology community as a whole. And that is that determining the amount of snow that we have and how much of that snow will eventually become usable water is a difficult problem. So to put an upper bound on our ability to understand and predict how much of that water we can use, we can take a look at the American River Basin in California, Sierra Nevada, which is arguably the most well-instrumented basin anywhere in the world. There might be some small research basins that are a little more instrumented, but as a whole, this is a pretty good metric for just how well we can do. And our year-over-year median error for predicting the amount of water we're going to get at some key reservoirs is around 18%. But the 1 out of every 10-year prediction error exceeds 60%. So about once every decade, we just have to throw up our hands and say we have absolutely no idea, right? And that leads to certain problems, such as the Lake Oroville Dam, the power plant there called the Hyatt Power Plant, had to shut down just at the end of last year due to the water levels being too low. And now part of that is a drought, but part of it is also being able to understand the amount of water we have so that we can better ration it throughout the year and be able to plan accordingly. And so this brings us to the problem we're taking a look at cracking, called the fate of snow. It's a 1-2 problem. The first is to understand exactly how much snow we have in these mountainous basins, right? That's our starting material. That's what we have to work with. Second, we want to understand how that snow turns into water, where it goes, if it sublimates, evaporates, infiltrates, or runs off into the usable rivers and so forth, down into a place that we can actually use it. So determine the amount of snow, determine where it's going. Turns out this is a very difficult, long-standing problem. Now, how we want to do this, go ahead, next slide. How we want to do this isn't to necessarily fly novel machinery or put new instrument devices in areas. That has certain value, yes, but what we want to do is take a look at the wide range of openly available remote sensing data sources. So there's 36 listed here that can have a potential relevant impact to help determine and predict the amount of snow we have in these mountainous basins, how much water we can get from them. And so we want to take all of these different data sets, work with the terabytes upon terabytes of data, different modalities, different resolutions, and for one combined universal prediction problem. And by and large, that's perfect. By and large, to date, this is often simplified for the sake of trying to incorporate it into existing physical models or trying to use existing tools. And so in order to do this in the BCI style, to bring the research, the core research together, the AI side and the hydrology side, we want to be able to use all of the data, all aspects of it, in a way where we can take as input all of this openly available data and predict these high resolution snow water equivalent or snow melt estimates in these regions, for which we have a very select amount of ground truth from flying LiDAR planes over certain regions. That's the exciting problem to work on. And from that problem, there are several different areas of core AI research that we're investigating and we're working on actively publishing in some of those conferences and communities that Rithwik mentioned as often underserved or historically underserved, places like NeurIPS and CVPR and so forth. And this list includes things like disparate multimodal data fusion, working along not so much a vertical scalability that we've seen in a lot of AI, but a horizontal scalability as well. Sparse to dense prediction, few-shot learning, physics-informed prediction, uncertainty prediction, all of these are intertwined in this really inspiring stew of problems and ideas. And perhaps most importantly is speaking with a scientist and going forward and saying, how can we add more scientific value? You know, you can take some existing tools and techniques, plug them in, get results. And they say, well, first of all, we need to understand the certainty around these predictions. And so one of the challenges isn't just necessarily being able to do point predictions like so much research focuses on in a lot of our fields, but working around predicting confidence intervals for these snow water equivalent and stream flow estimations. Identifying anomalous and contradictory data. So if you're working across all of these different data sources, you have to understand when certain data sources or individual data entries or items themselves could be contradictory or erroneous automatically, and attributing those to the problematic outputs. And that's really the final challenge, is both an uncertainty attribution, so being able to determine the uncertainty in these areas, but then being able to attribute it back to the original sources, and more of a deeper scientific understanding. And this has been a really high level overview of one particular problem called the fate of snow. Our North Star at the Bear Climate Initiative is to work on this broad class of climate related problems that we see having a substantial impact on so many different problems. As I mentioned, we went around and spoke with a number of different faculty and research groups, and we came back really from our very generalist perspective, hearing the same thing, which is I have all of these different data sources with different scales from different modalities and different spatiotemporal aspects. We call this OMS data, right? Like OMS data. And that's observational, multimodal, multi-scale spatial temporal data. And as an initial effort, we're working on developing methodology and tools based around these types of problems, both in the fate of snow and the many related problems, some of which you'll hear about today, in order to bridge this community. And part of the output in each of these projects is working towards not only data sets and benchmarks, but an iterative process to keep updating those and moving them along and progressing with the science and progressing with the AI community. Great, so that's a really high level overview, both of the BCI itself and the fate of snow. If you want to know more nitty gritty details, feel free to reach out to anybody on the AI climate team here. There's a website, we have a Twitter account, a fresh Twitter account, and really join us. There's roles for faculty, students, industry, operations, government, all sorts of wonderful folks doing lots of wonderful things. So please feel free to reach out. And I want to give a brief shout out to Bruce Riordan, who runs the Berkeley Climate Change Network. And this is an amazing collaboration here at Berkeley that a lot of different folks are part of. If the BCI isn't necessarily your focus or you fit into it nicely, there's people here at Berkeley, it turns out, in our community where you certainly will fit in, and we should be able to all come together. So there's wonderful folks doing wonderful things, and this is one aspect that we want to grow and continue to have in a larger community.
Thanks,
Let me
Alvarado.
turn it back over to Rithvik.
Yeah, thank you. That's our initial presentation. That's the BCI again, and using the fate of snow to highlight that if we didn't have the fate of snow as our lens, we couldn't solve some of these, or it'd be much harder to solve some of these interesting AI problems. So let's work on both of those together. Let's have the meaningful impact in climate while also having a meaningful impact in AI. So please join us. The rest of the session today is focused on showing you more problems in the space of how AI and climate change are more intertwined than you think. And there's also a fantastic panel that's going to talk to you about, well, if you've never worked on AI climate research before, how should I, a random researcher out in the field today, start working in this area? And instead of thinking of it as a pivot, let's think of it as a complementary thing. Like, how can I start viewing the same problems that I've always been thinking of with just this different lens? And with that, I'd like to invite Trevor up to introduce some of our lightning speakers. I'll pull up some of the slides here.
Oh, well, I'm just going to introduce you so you can get started. Oh, we're skipping you. I have an out-of-date schedule. So we go straight to Daniel? Okay, well, we have a series of lightning talks on cool projects in addition to the fate of snow. And so we'll hand it over to Dan.
I don't usually use these. Where does this go? Okay. Hi, everyone. I'm Daniel Rothschild. I'm a PhD student in the computer science department. And today I'm excited to tell you about some work I've been doing with these great collaborators here. I can get rid of this welcome. Yeah, so these are people across computer science and also chemical engineering and material science. And we've been working on accelerating computational chemistry for materials design using machine learning. So first, I just want to motivate the space here. Why do we need to accelerate materials discovery? And Ritwik mentioned this before, but there's all sorts of applications where we need new materials in order to make sustainability not only less costly, but maybe even profitable. So just as throwing a few examples on a slide here, we need new materials for batteries, for EVs, and also for grid-scale energy storage, cheaper, lighter, more efficient solar panels, materials to capture carbon dioxide before it even gets into the atmosphere, and catalysts that can convert that carbon dioxide into useful materials like fuels and industrial chemicals. So we're going to zoom in on just one of these, carbon capture, as an example. What does this actually look like? Well, you have a smokestack with flue gas coming out of your coal power plant, and you want to put some material in the smokestack that pulls out the CO2 and separates it from the rest of the gas that goes out into the atmosphere. What do we actually use for this? Well, a promising new class of materials for this are these nanoporous materials. I'm showing here an example of what's called a metal organic framework, which is one of these porous materials. And these actually sit in the flue gas stream, and they have these little pores where the carbon dioxide molecules just fit and other things don't fit. So people have been working for a long time on designing these materials to be better at capturing carbon dioxide. And the central part of doing that is computational modeling to figure out, for example, how big are the pores, and are they the right size to capture carbon dioxide? So a workhouse calculation that people do as sort of a starting point for any kind of analysis for this is called density functional theory, or DFT. And what DFT does is it takes a guess for the configuration of where all the atoms are in your material, and it finds the lowest energy state, which is the configuration of the atoms that has the lowest energy. And the reason this state is important is because the lowest energy state is the state that your material is most likely to actually adopt in the real world. And because based on the lowest energy state, you can calculate properties like things that are important for carbon capture, or for solar panels, maybe the band gap for calculating efficiency, that sort of thing. So we need to do this. People are running DFT calculations all the time, but the problem is that these calculations scale with the number of electrons cubed in your system. And this makes it very hard to study large systems or many smaller systems, since it's very slow. So our goal is going to be to accelerate this with machine learning. To show you how we're doing that, I just need to quickly explain how density functional theory works at a high level. So it takes your initial guess for where all the nuclei are, and then it calculates what are the forces on the nuclei if it's in that position. And then it adjusts the positions of the nuclei so that they move in the direction of the force. And it does this over and over and over again until you get down to the lowest energy state, which is also called the ground state. So this is the iterative calculation we're interested in. And we're proposing to accelerate this with machine learning as follows. Take all of the early steps in this calculation and replace them with a machine learning model. And then at the very end, you can tweak your answer with a few iterations of density functional theory. And what's nice about this is that DFT is very slow for all of the iterations, but if we can replace most of the early ones with machine learning, that will speed things up. And for reference, there's maybe 2 or more orders of magnitude on the table here in terms of calculation speed up. The other nice thing about this paradigm is that because you're running DFT at the end, you're going to get the exact same answer whether or not you use machine learning. And this is super important for getting adoption from scientists because they don't trust machine learning. And so if you set things up like this, and as a machine learning researcher, I can say that that's very valid. So if you set things up like this, this is great because they don't have to trust it. It just speeds up their calculation. Okay, so how are we actually going to train this? I've spent most of my time explaining the setup, so I'll just quickly go through our method, and I'm happy to talk to people during the reception. But our training objective is a denoising objective. We take our ground states that we have training data that we can use here of ground states, and we add random noise to them. And then we use our machine learning model to predict back down to the original ground state configuration. This is a classic denoising setup. And what's really nice about this is that we can just take our ground states, we can add a whole bunch of random noise in different ways, and then our machine learning model has lots of data to train on. So there's a few things that we found to be really important to make this work. The first is what's called equivariance, which means that if you rotate the input to your neural network, we want the network to be such that the output rotates or translates in the exact same way. And the second thing is this iterative calculation. So we take inspiration from existing numerical methods that sort of do things step by step. And instead of having one monolithic model that predicts from the input to the output, we actually split it up into a whole bunch of models. And this drastically improves performance because each model is maybe only working on a subproblem. Yeah, so again, I don't have time to go too much into our preliminary results, but here's a plot showing that our initial guess structures are very suboptimal. They have high energy suboptimality, and after we relax them with our machine learning method, they get to much better energies. But I'd be happy to talk further later in the program. Thanks.
Next up is Sherry Wang.
Okay. Hi, everyone. I'm a postdoc at Berkeley. I did my PhD at Stanford, graduated last year, and now I'm a postdoc in the Global Policy Lab working with Saul Xiang. And this is a project that I'm currently doing with Saul and a PhD student named Hikari. So it's still pretty early. We started this maybe 4 months ago. And the idea is to measure CO2 emissions from power plants using satellite data. So the reason that we're doing this is that this might come as a surprise to you, and it certainly did for me, that humanity currently lacks good top-down estimates of CO2 emissions. So right now, the data that we have on CO2 emissions are mostly bottom-up, kind of a lot of them are self-reported emissions. And a recent Washington Post investigation actually found that if you add up the emissions reported by 196 countries around the world, and then compare that to some independent measures of total CO2 emitted by all of humanity, you actually have a really large gap ranging from 8.5 to 13.3 billion tons of CO2. And that's huge because total CO2 is only about 45, 50 billion tons. So this is big enough to definitely move the needle on how much the Earth is going to warm. So this really highlights the need for objective, transparent, accurate, and high resolution, aka like disaggregated country level, or ideally even finer resolution emissions measurements. There's multiple ways you can get at those measurements, but one that I'm going to talk about today that we're focusing on in our project is using satellites that can measure column CO2. And they do this via spectrometry, and our idea is to use that data and machine learning to then back calculate or do like the inversion problem of how much was emitted by sources on the ground. So here are some examples of current satellites that monitor CO2 from space. The most well-known one is probably OCO2. And there are also a lot of instruments planned in the next couple of years from the UK and France, or JPL and Planet Labs, as well as the European Space Agency. So prior work that we're building off of has shown that OCO2 can estimate individual power plant emissions by taking these overpasses of OCO2, which is what the figure on the very left is showing. You take the overpass, then you look at the CO2 enrichment downwind of the power plant. You compare it to the background CO2 in the surrounding areas where the plume from the power plant didn't blow. And then you do a Gaussian plume model, you fit that to the enrichment, and then you infer what the power plant was emitting at that moment or in some amount of time prior to the OCO2 overpass. However, this work showed that it's possible to do this to high accuracy, but only in very limited situations. So these two existing works from Ray Nasser and others showed that they can back calculate the emissions when the wind is blowing along the direction of the swath. The terrain around the power plant is flat and there's no clouds at all anywhere along the swath that they're considering. So they actually only covered 7 power plants in their first paper and 14 power plants in their paper from last year. To us, this seems like there must be a lot that's being left on the table because there's a lot more data being collected by these satellites. A lot of them just don't happen in these ideal conditions that we're comfortable using this Gaussian plume model to do the inference. So we looked at all OCO2 overpasses that pass within 10 kilometers of any power plant in the US, and that already gives us over 10,000 overpasses. So not all of those are going to be usable because some of them, the wind's not even going to be blowing onto the overpass at all. But this is already even taking a % of those, that's already a lot more data than researchers have ever worked with before. And then the EPA monitors hourly power plant emissions, and so we can try to relate the OCO2 overpass data to the EPA hourly emissions to try to predict what the emission was at the power plant in these more complex settings. So that's what we're working on. And this problem also involves pulling a lot of other data sets like Colorado mentioned in the Fate of Snow presentation. So we are also interested in pulling wind data sets or elevation data sets, satellite imagery that can tell us about land cover, and so on. And the idea is to combine these multiple data modalities to then predict emissions of the power plant. So this is still pretty early work, but we're excited to see how it goes, and I'd be happy to talk more about it at the reception. Thanks.
Excellent. Yeah, I think we're going to do questions at the reception, or maybe we can have questions at the end of this session. The next presentation is by Hari Das, Data-Centric Machine Learning for Smart Buildings.
Hi everyone, I'm Hari Prasanna Das. I'm a PhD student in Department of Electrical Engineering and Computer Science, working with Professor Kostas Panos. Today I'll be talking about data-centric machine learning for smart buildings. In particular, this is my research, but I'll not go deep into my research, but I'll mostly cover a general overview of smart buildings and how machine learning is being applied in this field. And I'll also go a little bit into how my research particularly focus on the data-centric part of it. So a survey from the US Energy Information Administration says that buildings account for 39% of total energy consumption and 76% of electric use and a lot of greenhouse gas emissions. So as all of us here, we all know that we spend around 90% of our time in buildings, right? Like we all are either at our home or at our office. So either we are in residential buildings or we are in commercial buildings. We are doing something inside a building that decides a lot of about how the thermal environment is, how the security is, and a lot of energy goes into maintaining that thermal energy and that environment that is suitable for you to stay in the building and be productive, right? And that energy contributes to a lot of greenhouse gases, and such high levels are rapidly increasing throughout the world. Now, if we see the main picture, many people say that buildings are a low-hanging fruit when it comes to using machine learning or using any other technique to improve energy efficiency and solve or reduce the greenhouse gas emissions. So the goal here is to optimize building energy use while maintaining occupant comfort and productivity. And doing that can significantly reduce the building carbon footprint. Now, if we go a little bit deeper into what smart buildings are and what are its components, You'll see that it has lighting control, it has media control, it has energy generation, which a lot of us might have interacted with folks from or have heard a lot in the news about how our energy is generated or being transported to or distributed to us. It also has control of other devices inside buildings. It has waste management. It has security control. And one of the major, one of the major system that is HVAC control, which stands for heating, ventilation, and air conditioning control. It takes a lot of energy, and this is one of the key areas that people focus while trying to optimize the energy uses, right? And if we go a little bit into what kind of data are available in smart buildings, they are usually time series, tabular, and vision data. And we usually have environmental variables that are temperature, humidity, and air quality. We have energy related, that is heating, ventilation, and air conditioning operation. We have lighting, we have plug loads, and we also have information related to occupants, which are their behavior, their presence, their location, and their thermal preference, right? Now, let's go into how or what kind of machine learning techniques have been used in different applications in smart buildings. And whatever I cover here is not inclusive of all the applications that machine learning can offer, but some of the instances of applications. One of the uses is fault detection in different equipments that buildings has. And usually the anomaly detection techniques that we commonly develop using out of distribution techniques, those are also used for fault detection. We have thermal comfort understanding and prediction. We try to understand when people will be comfortable thermally in a building. And once we have learned that, we try to predict that and include that prediction into building control so that people are happy, as well as we have some band with where we can optimize and reduce the energy uses. And we commonly use multi-class classification, and this also goes into control. We have building control and grid applications, for example, demand response, which means we get energy from the grid, and the grid gets energy from either renewable or non-renewable sources. And if we can optimize when people are using the different equipments in a building, you'll be able to have or encourage more use of renewable energy, as well as you'll be able to plan better on how much to generate and how much generation will be sufficient for everybody in the area that this generation covers. So in this field, we usually use time series forecasting, and for building control applications, there have been a lot of traditional control mechanisms that are used, but recently reinforcement learning has found applications in building control. We also have security and privacy because the data that gets processed by systems has data that corresponds to privacy of people. So we have privacy preserving data sharing and adversarial robustness here. We have occupancy or activity detection. So if we can understand how many people are in a room or what they are doing in a privacy preserving manner, we'll be able to control a lot of equipments in a smart way, as well as energy preserving way. And in this, we use classifier design that is based on usually Wi-Fi CSI images. CSI stands for channel state information that is particular to Wi-Fi devices, or CO2 sensor data, or people have also used cameras, although that is a bit debatable because cameras come with privacy challenges. Now, going a little bit into my own research, I focus on the data-centric part, and I try to see where the data is lacking, right? So I try to see, for example, in fault detection, we have limited data for rare events. That is a challenge, right? In thermal comfort, we have limited data for rare cases, like aged or frail subjects or over or underweight subjects. We have issue of generalization, like a developed machine learning method that works in one building or work for some person might not be transferred directly to other person or other buildings. There is limited data diversity. And in control, we have insufficient data-driven building performance models because of lack of enough data covering some special cases. We have limited data for rare events or attacks. And we also have issue of generalization in occupancy or activity detection. Now, if we kind of combine these challenges, we see limited data for rare events, scarcity of labeled data, domain discrepancy that also has unavailability of labels across multiple domains. And my research tries to come up with techniques in machine learning that might be familiar to all of you, such as conditional synthetic data generation that I try to use to generate some data for low-tail distributions, long-tail distributions. And I also use domain adaptation literature as well as style transfer literature to generate data as well as classify data into particular classes across domains. So the good part here is all the techniques that, or all the models that we like StyleGAN or DALI, might have a direct uses in smart buildings. So I would encourage you to look into it, and I'll be happy to chat more.
Great, thank you very much. And our last presentation in this session is from Ankur Mahesh, who will be presenting Detecting Atmospheric Rivers Across Climate Datasets and Scenarios.
Hi, my name is Ankur, and I'm excited to talk to you all today about atmospheric river detection across a range of climate data sets and scenarios. I'm a PhD student here studying atmospheric dynamics. Atmospheric rivers are long, narrow columns of moisture in the atmosphere. They're important for parts of the world like the west coast of the United States because they alleviate drought. In particular, the western part of the United States gets at least half of its rain in any given season from an atmospheric river. But on the other hand, a very intense event can lead to billions of dollars of flood damage. In the Earth system, and from a climate science perspective, they're also an important mechanism of poleward energy transport, which allows the Earth to maintain energy balance. Circled in red in that satellite image is the atmospheric river, which is marked by that long, narrow column of moisture. And in particular, this image is important to me because we had an anomalous atmospheric river come in May a few years ago, which was the day I graduated, so it's a little poetic. So in existing work, we've trained neural networks and convolutional neural networks to detect atmospheric rivers in historical observations. It's important to note that there isn't a fundamental first principles definition of what an atmospheric river is that's grounded in fluid mechanics. And instead, experts have to manually either draw contours of atmospheric rivers in a climate simulation, or they have to define a set of thresholds and tune them by hand in terms of water vapor transport, total water vapor, and a height to width ratio. So in existing work and historical observations, we trained a neural network to take in water vapor transport as its input and as its output to predict the proportion of algorithms that would find an atmospheric river. You can see that proportion shaded in white for more confidence that there's an atmospheric river at a given location. But this begs the question, can we extend the neural network beyond historical observations to new data sets? Out of the box, the neural network does not generalize from historical observations to historical climate simulations. These are run with the same historical forcings, so there's no reason for there to be different performance. But if we take the neural network that we've trained on observations and apply it to a historical climate model out of the box, the performance is generally that the detections are too low. In this particular example, you can see circled in green that the neural network almost entirely misses several atmospheric rivers off the coast of South America near Chile and Argentina. So to tackle this, we use a method called style transfer, which is something we've seen in filters on our phone, where we can take a photorealistic image and convert it to the style of a Vincent van Gogh painting. And you can see that being applied here to the Golden Gate Bridge. Some work from Lee et al. Identifies that style transfer is a form of distribution alignment. So it's matching the feature distribution between the style image, so the painting from Vincent van Gogh, and the generated image, which is in this case, the Golden Gate Bridge, in the style of that painting. But this distribution alignment is also useful for climate, for extending our neural network beyond observations to new data sets like simulations. So the climate version of this is to convert the style of images that are done on climate simulations into the style of image that are done on historical observations. And you can see that when we apply this method, the neural network performance is more in line with historical observations on the historical climate simulation, and it's no longer missing those atmospheric river events off the coast of South America. This enables us to ask and hopefully answer some important questions about atmospheric river activity. For example, in idealized models where we don't have those existing detection algorithms already run, we can study the dynamics of atmospheric rivers and how they engage with specific atmospheric processes. So in the simulation that I'm about to run on the left, the bottom plot shows how there's a jet stream, and wave-like motions in the jet stream create atmospheric rivers. So let's watch. As the simulation runs forward, the wave that forms in the jet stream causes atmospheric rivers right around here, and then eventually the atmospheric rivers dissipate. But this allows us, using style transfer, to explore how atmospheric rivers behave in such an idealized set of physics that govern the Earth's climate. For example, the contours shown in red here are the neural network using style transfer to detect the atmospheric rivers in an idealized context where we don't have existing labels from existing algorithms. This also allows us to explore how atmospheric rivers will behave in fully complex, every single fully coupled models of the Earth's surface with both the atmosphere and the ocean. So here, using the neural network trained with style transfer, we can explore how atmospheric river probability changes in worlds with varying degrees of emissions. Here, shown in red, indicates that there's greater likelihood of atmospheric rivers. And this is the first step that we need to explore how atmospheric rivers and the resulting floods and droughts will change as our climate changes.
Thanks. Excellent. Let's thank all the speakers. What an excellent session we just had.
Also, I'd like to highlight that we did not prime anyone on what to present. We're just like, hey, 4 of our friends, you want to show up and talk about your work? But I hope you're able to see the exact areas in which working on these climate problems necessitate improvement in core AI research, which was completely unprompted. All of them just came up with that on their own. So pretty cool stuff.
I think we're going to set up for a panel right now that Medni is going to host. As we're doing that, I did want to throw it open for questions. We sort of didn't leave any time for questions during the presentations. If anyone wants to shout out a question now, either about any of the talks we just saw or about the whole BCI initiative, happy to try and field those. Otherwise, are we going to bring all the panelists up and have them sit up here? I think we will, right? If you're a panelist, please join us in the chairs that you see assembled there. If you have a question, please shout it out or speak it from online.
We don't need to screen. We can put it up.
And I think what you saw in the presentation so far is essentially a taste of the kind of projects that we see at the intersection of AI and climate science at Berkeley that we're excited to be supporting and mentoring through the BCI. And now I think we're going to hear from some of the luminaries in the field at Berkeley and in industry to share their thoughts on a path forward. So I will hand the microphone to a panelist, and you're going to have to manage this microphone.
Thank you.
Okay. Right, okay. This is on. Oh, perfect. Hi, everyone. I'm Medani, and I'm very happy to be here to host the BCI launch panel today. So our session, we have 5 researchers working on climate change related problems, and we have a bunch of questions that we plan to ask them. But if at any point anyone in the audience has any questions, please feel free to interrupt, raise your hand, and we'll try to get around to that. So just as a reminder, our session today is going to be for 45 minutes. So please keep your answers to maybe a minute or so. So with that, let's get started. Could each of y'all maybe share a bit about your background and how you ended up working on problems in this space? And we'll start with Caleb.
Awesome, thank you. Yeah, so my name is Caleb Robinson. I am a research scientist at Microsoft's AI for Good research lab. I guess I got started in this space during my PhD. My PhD advisor, Bistro Delkina at USC, was heavily involved in the computational sustainability research topic. So I took a lot of inspiration from her, and I've kind of built that into now starting my career at Microsoft. And at the AI for Good Research Lab, we work with partner organizations like NOAA, the Smithsonian Institute, World Resource Organization, World Bank, on projects that they have that they need a little bit of kind of data science or research scientist expertise in order to solve. We communicate with them and kind of build these into long-term projects where we aim to open source our code, results, data sets, and so on. And some of these projects definitely fall under the realm of kind of climate change related. So I guess that's who I am and what I do.
Yeah, thank you. Off to Dan.
All right. Hi, all. I'm Dan Feldman. I'm a staff scientist at Lawrence Berkeley National Lab. I've been in the climate change research space for a while now, since grad school. So yeah, that was about 15 years ago or so. And you know, I've just had the pleasure of seeing the field advance quite dramatically. Also, the challenges really increase quite dramatically. Thinking about the CO2 emissions that we've been hearing about today, the numbers were a lot lower when I started, and I continue to have to look that up. I'm here because I've had some really nice conversations with Colorado Reed and a few others on this Fate of Snow project. And I'm heading up a research project in the Colorado Rocky Mountains at a ski resort. So come on by. But yeah, seriously, it's and we're really interested in the Fate of Snow. And we're collecting a lot of data on snow. It's very complex. It's very heterogeneous, and all of the points that Colorado raised are very relevant to us. And so we're really interested in getting AI expertise help in analyzing our data and developing insights. So thanks.
Hi, everyone. My name is Aditi Krishnapriyan. I'm a new faculty here at Berkeley and at Bayer. And my research is at this area of physics-informed machine learning and scientific machine learning. So how can we develop new machine learning algorithms to improve generalization, specifically in the scientific domain? What are the inductive biases we can add and develop? And my background is actually in physics-based modeling. And I think a lot of climate change is really revolving around that, like numerical methods, quantum mechanical simulations, differential equations. And so I think it's always been of interest to me to be in this climate change domain, and it's definitely influenced my career. And now I think there's some really nice opportunities going forward to take the tools that we have from traditional physics-based methods, but also combine them with machine learning methods. So I'm excited to build this group at Berkeley going forward.
Thank you.
Hi, I'm Matt Utendale. I'm a director in the AI research group at Meta. And I'm actually fairly new to the climate space. Most recently, I was running the perception team for our Oculus headsets. And I wanted to make a change, looked around Meta to see something interesting to do. I was particularly interested in climate and addressing the climate problem. And I realized that at Meta, we actually had quite a few people in the company working on climate, between our net zero policy, trying to get to net zero by 2030, scope 3 net zero by 2030, between our 100% clean energy. We have a climate science hub on the Facebook app. We have a commitment to be water negative by 2030. So there's a lot of people in the company working on AI. And we had one small project in the AI research group called the Open Catalyst Project. So I latched myself onto that, and a few of us formed a bigger team around that called AI for Science. And we're looking to ramp that AI for Science effort up, work on climate problems at Meta. Open Catalyst has given us a terrific template. Open Catalyst is using AI for material discovery around green hydrogen catalysis. And that's so far been a super successful program for us. We've got great collaborators in academia and in industry there. So we want to do more of that. We're looking for more climate problems to solve and looking to apply the resources that Meta has as appropriate to climate.
Excellent. My name is Dara O'Rourke. I'm a professor in the Department of Environmental Science here at Berkeley, but the reason I'm on this panel is over the last 6 years, I have been helping Amazon set up their sustainability science program. which started off first by building their first carbon models company-wide, which Amazon is really like 30 companies in one globally. And then building from there to the climate pledge. Amazon took a pledge to be net zero carbon by 2040, which has kicked off much more detailed modeling on both decarbonization of the global company and on nature-based solutions to offset and remove carbon where they can't eliminate it. So we're using AI both in the decarbonization of the business, which I can talk about, and also in traditional geospatial uses for avoided deforestation, carbon removals, nature-based and technological. We created a $100 million nature-based solution fund called the Right Now Climate Fund, and then a $2 billion fund for investing in low carbon technologies. And in both cases, we're using software and hardware to try to solve climate problems.
Okay, thank you so much, everyone. Yeah, with that, we'll get started with our first question. So today we launched BCI, which focuses on using AI for addressing climate change problems. So what role do you see AI playing in solving climate change? And we'll start with Aditi. Yeah. Okay.
So I think, like I mentioned, I think a lot of the core of climate change problems are really rooted in physics-based modeling. Right now, a lot of that modeling is really intractable when we want to model realistic scales and also do this over very long time scales. Like, can we forecast a lot in the future? And I think because of that, because of this really need for efficiency there, that's definitely one of the big areas I can see machine learning playing a large role in speeding up these simulations. But also at the same time, I think it would be nice if we can get some interpretability from that too. So can we actually learn something from the data? Can we learn the laws of physics from the data? Can we learn the symmetries in our models from the data and actually use that going forward?
Okay. And Matt? Yeah.
Yeah, sure. I'll give a call out to Priya Danti wrote this paper called Tackling Climate Change with Machine Learning. That paper is going to do a much better job than I can. So I'm not going to try to enumerate everything. And I think, Jennifer, you were a co-author on that, right? So that's pretty cool. So that's an awesome paper. I refer everybody to that in terms of the large list of things that we could do. So I'll maybe focus on the things we're doing at Meta. So, when we're looking to apply unique resources that we have to this problem. So one thing you'll see many of the companies, these large tech companies in the space are trying to map the world. And we're no different in terms of building a map of the world for our AR ambitions, right? We want our AR glasses someday to be able to recognize what's out there in the world. So we've got this highly detailed map of the world, and there's all sorts of AI that you can run on that could benefit sort of climate solutions. And so that's one place that we're looking heavily at. There's one example of that is population density map that we recently released. It's the density of human population on Earth. We used a combination of high resolution satellite imagery along with our social data and able to use this, produce this this population density map that has now been referenced in many research papers, and we've open sourced all that. Another one is I briefly mentioned the Open Catalyst program. There, we one of our big contributions there was just compute hours, right? We ran 200 million CPU hours to create this unprecedented data set for for catalysis. We had a nice presentation of DFT earlier, and this is in that same vein, same line of work. I think I'm forgetting. So yeah, and then actually we have sort of big carbon footprint in our buildings, so especially data centers. So we've recently done AI to formulate cleaner concrete, to create cleaner concrete, so less carbon intense concrete. So those are the three examples of where at Meta we're applying AI to climate problems.
Okay, thanks. I guess I'll have a follow-up question for you. So I guess where do you see is the biggest challenge? So these are three great examples. Like, is the challenge in like coming up with more problems, or like taking this to completion, or
Yeah, I'd say that the challenge is, where we can uniquely, where our resources can be uniquely used to solve some of these problems. I think, just picking the problems to work on, I think to me so far is the greatest challenge.
I see. Okay, thanks. Next, I guess we'll do Dan. Yeah.
Okay, thanks. Yeah, so I wanted to second some of the things that Aditi said about about the role of physics models. They're very important, but they're also there are some fundamental intractabilities in terms of advancing them. Being able to run a process model at the resolution that it needs to run at to resolve processes related to snow is wildly infeasible. If we want to do it across the Colorado Rockies or across the world, exascale computing is insufficient. And so we need to put on our thinking caps a little bit and recognize that the way that we represent physics is important, but that there also needs to be some connective tissue between the observations and the models. This was highlighted with respect to the Fate of Snow project in a recent paper just before COVID that pointed out that that our ability to understand hydrology in mountains is limited to the extent that our process models are actually doing a better job than observational products in forcing hydrological models. So that sort of puts the whole scientific approach of like gathering new data sets and testing models in a difficult place. And so that's where, I think there's a really, there's a lot that we can do here as at the same time on working with domain experts in snow science, in atmospheric science. I hear a lot of researchers asserting that they can do AI themselves without much background in it. So I think it's nice to be here and work with people who have that background and build that bridge that we've been talking about.
Nice. Yes. Building the bridge. Okay. So I'm going to go on to the next question, and I want you to pass the mic to Dada. Yeah, thank you. So we've talked about like curbing carbon emissions. People say that this is strictly policy related, and the bottlenecks are not in research and technology. What are your thoughts on that?
I think that's kind of a silly statement.
Okay, nice.
Clearly, we have lots of work to do on all fronts here. And so we obviously have policy challenges, but we also have politics challenges, power challenges, incumbency challenges, and then we have some real technological challenges. So, on the easy public version of we know most of the things we need to do to solve climate change, probably 80% right. Like we know 100% renewables, electrify everything, et cetera, low carbon concrete, steel, plastics. But on all of those, we need huge investments in scaling and driving down costs and deployment and making these work in contextually relevant ways. We also do have areas where we have no solutions, where we actually have grand challenges in climate and in decarbonization. We don't yet have affordable low carbon concrete or steel or plastics or aluminum. We don't have low carbon air freight. We don't have low carbon compute. We don't have zero carbon integrated circuits. There's lots of things that we do have to go invent. And there's huge benefit from early lab research to startups, to scaling it through large companies, to government performance standards, taxation standards. So we've got a lot of work to do on all fronts. Policy is the one I think we're the most blocked on right now. So I would not look to Washington, D.C. or even most capitals right now to push it. We really have to be pushing research and action on the ground to drive so policy will catch up.
I see. Okay. Anyone else has any counterpoints to that?
Yeah, I think I would agree in that. I think a lot of the factor is actually economic and commercial. And if we could actually get to the point where things are more economically viable or like more sustainable options are more economically viable, we might actually see adoption from maybe like a more unified view here.
Caleb, yeah.
One thing that I think not to that we're particularly blocked on the policy side, but one thing that AI and machine learning models can do is help monitor some of these processes in the background as we work out the roadblocks on the policy side of things. And kind of geospatial machine learning can play a huge role in that, kind of keeping everyone updated on the status things is, I think, a very important component to this.
Okay, so do you think like if policies is not the challenge right now, it would become the challenge going forward, or, you know, do you see it as not so much of a big challenge at the moment? And
Who's the question?
Oh, yeah, you can go ahead.
I mean, I definitely think we're blocked in some policy parts. Maybe not others. Does anyone else have thoughts?
Yeah, I mean, I'll take a cut at it. I don't think that climate is such a huge problem. Right? It's like there's so many different dimensions to it. There's so many different ways into it right now. I don't think we can blame policy right now for being the only blocker on this, right? I mean, there's if you look at direct air capture, there's like Meta, Stripe, Google just put $1 billion towards direct air. That's good policy. I think that those $1 billion aren't going to directly solve direct air capture. We need scientists and engineers to go out and solve that problem now. So similarly, the Department of Energy put $3.5 billion towards these DAC hubs, right? So there are policies out there that enable good progress right now. Sure, like we could point to some bad policies out there, but I don't think that we're blocked on policy right now. There's a lot of work that we can do, and to me, it's time to start building. And so.
Okay, yeah. Looks like, Dara, did you have anything to add to that? Or?
Yeah, I think we're in agreement. I think, unfortunately, we're in a very bad position on policy. I mean, basically, the #1 proposal of this administration was blocked in Congress, largely by the honorable senator from West Virginia was able to block it. So we have basically our policy is captured by incumbent interests, by fossil fuels, by big automobile industries, by big material industries. So we are in a difficult position in policy. California is leading. There are some other countries leading, but this is a real problem, and it's a serious problem. And that maybe not the problem for this topic and this debate, but I think where we agree is we do have to get universities, we have to get companies, we have to get startups, we get the rest of the world to just move and solve these problems and take them on. And we can't really wait for DC, unfortunately. We have to move past it, while hopefully it will catch up.
Okay. Dan had something to add.
I just wanted to add one other aspect is that that we're still advancing the predictability of our Earth system, and will continue to do so. A large number of the scientific community is focused on advancing Earth science, but the Earth is a very complicated and interconnected system, which we currently understand a small fraction of, and can use our tools that we're building here to advance dramatically. And that's really why it's so important to work hand in hand.
Okay, thanks so much. I'm going to move on to the next question. So at BCI, we're talking about interdisciplinary research. So this is definitely hard, trying to get researchers from different backgrounds to collaborate, work on new problems. So have you managed to build interdisciplinary research, and how did you go about doing this? And we'll start with Dan.
Okay. Yeah, thanks. Yeah, so I think interdisciplinary science is something that's very important. It's also a lot easier said than done. So who is going to raise their hand and say, let's not do interdisciplinary science? Like nobody. But when it comes to funding, when it comes to papers, it's sort of a situation where, oh, my discipline's a little bit better than yours. And so that's a challenge. And so I've seen in proposals, you get crossfire from both sides. I've seen in papers the same thing. And so at the same time, disciplinary research is very important, and it's very important to lead with the leading edge of disciplinary expertise, but connect those together like we're doing hopefully here. So that's been my perspective, and clearly the interdisciplinary nature of climate change research necessitates us to work together.
Okay, we'll move to Caleb next. So, you know, at like Microsoft, I'm sure this is a big challenge, and yeah.
Yeah,
tell us more.
so at the AI for Good Research Lab, pretty much all of the projects we work on are interdisciplinary. And I think the number one kind of thing for success is focusing on communication up front. You really have to develop a lot of time to speak the same language as the domain experts that you're working with, because often even kind of things like precision and recall metrics that we're all familiar with have no meaning or have different names with the partners that we work with. So communicating the limitations of AI, of the models, figuring out what exactly the problem that you need to solve, that a model would be useful to kind of put into action, are all things that require communication. So really taking the time upfront to go through basically a checklist of things, I think really contributes to the success of interdisciplinary collaborations.
Okay, I see. So like there's probably a bigger threshold to overcome in the initial stages of a project, but once you get the ball rolling, you feel like everyone's usually on board.
Yeah, it's like a time investment up front. Make sure everyone's on the same page, make sure you agree about what the model is supposed to be doing, make sure you're speaking in the same terms, everyone is kind of clear with what's going on. And that really kind of helps success in the long run.
Okay, nice, good to know. Thank you. We'll pass the mic to Matt. Yeah.
Yeah, I coming from a big company as well, echo a lot of what Caleb says. I think, so I tell a story. I'm on the board of this wildlife conservation group up in Seattle, and I came in, from Microsoft thinking I was going to have this big outsized impact on this little organization that does wildlife conservation. I realized pretty quickly, I didn't know anything about the land management. I didn't know anything about any of the conservation science that these people were running. I didn't know anything about nonprofits, and that they quickly realized that. And I was like tasked with determining whether to run Teams or Slack or like that was so. The lesson I took from that is, come into these interdisciplinary collaborations humble with a desire to learn and understand, what you have to bring to the collaboration. I think in our working as an AI practitioner, I think what we have to bring is this ability to know how to utilize enormous compute at scale. That's one of I'll refer to the Open Catalyst project again. That's something that we contributed there. We know how to manage data. We're like expert data labelers, right? Like, we've had to solve that problem over and over and over again. So managing these enormous data sets is just a skill set that AI practitioners have. And I saw that in Colorado's talk. He listed all these data sets. And I think they're going to make some real significant, do some real significant work there in terms of advancing the ability for those data sets to interoperate. And also these AI models that we've built in other places. Like I was really psyched to see style transfer show up in an atmospheric river talk. I'm like, I've worked on style transfer at some point. And I thought it was this trivial thing, and so now I feel much better about it. Like, wow. So I think just understanding sort of what your skill set is, what you have to bring to the collaboration, and being upfront about that, and just being humble and willing to learn. I think what I've how I've approached these things.
Thank you.
Yeah, our most successful interdisciplinary collaborations inside Amazon have combined a subject matter expert, someone who has a PhD in life cycle assessment, with a data science expert or an AI expert, with a product manager with a customer obsession. So that kind of technical competency plus deep subject matter plus focus on a problem and a user and decisions has been when it really comes together for us. Just like the natural scientists can pretend they're AI experts, the AI experts can pretend they're natural scientists, right? We really need this combination of people working together, and the technical competency plus the subject matter deep expertise and humbleness of these things, but then focus on an actual problem and decision support tools, I think is when magic occurs. And that's very difficult for any one individual to do, but you can actually learn it as a person if you want to, but also teams work better.
Yeah, that is good to know. Could you give us like an example of one of these projects that you worked on, and like, people from different backgrounds, and like which areas they came from?
Yeah, so one that is a little bit different than the one. So as I said, we're trying to decarbonize Amazon. It is a retailer, it sells products. So we're trying to use artificial intelligence, machine learning to identify more sustainable products and customers who want those products or attributes of those products. So we're applying that in a way that we need people who actually know the science of sustainability. What is a sustainable product? How would you actually understand that? That's this field of life cycle assessment with data scientists, machine learning experts, applied scientists, we call it, and then with people who have this customer obsession, this kind of ability to understand how a person actually makes a decision about purchasing a product. That's not something a nerd inside academia is going to be very good at. You really need someone who thinks like a consumer all day long. So we've been able to build this kind of ability to identify people and products and attributes and get better over time and hopefully decarbonizing consumption through that combination.
Yeah, nice. I like that approach because you have the goal set as like a common one for everyone involved in the project right at the beginning. Otherwise, I can see how there can be a lot of issues that arise. Yeah. Yeah, we'll move on to the next question. So if a student or a fellow researcher wants to start working in this space, like using AI for climate change, what is the advice you would give to them? And we'll start with Aditi.
So I think one thing I've noticed is to really make these interdisciplinary collaborations happen, activation barriers have to be sufficiently low on all of the different sides. And I think what's really exciting now is that we're seeing a new generation of students, not just specializing in one area, but trying to actually specialize in multiple areas and trying to build expertise across areas such that they can tackle the problems of two different domains, but with a combined effort. And so I think on that note, there's some really exciting opportunities at Berkeley. I think, there's really expertise in many different departments. And so I think there's a lot of really nice classes now offered through multiple different departments. There's now a CDSS as well, which is really making an effort towards that goal. And I think just being involved in BCI is really one way to maybe meet people working in a domain that you would like to work in or like to interface in and build expertise in both areas. And I can add to that I am taking students, so if anyone's interested, yeah.
Do you think there are any like downsides to starting in the space if someone's just beginning their PhD? Yeah.
Yeah, I think like starting in like an interdisciplinary space.
Yeah, exactly.
Yeah, so I'd say, yeah, it's a little bit tricky to start interdisciplinary right off the bat because sometimes it helps to have a foundation in one area and then bring in the next area. So I'd say that it still helps to specialize at least in the beginning, but I think definitely over the course of a PhD, you can absolutely bring in other expertise, other domain. For example, like Daniel, who gave the talk on materials design, he has a background in physics and in computer science, and I think has really merged those backgrounds very nicely together.
Thank you. Okay, Dan, what are your thoughts on that?
Yeah, and I guess I would advocate as well. There's a large number of classes and expertise on the the physical sciences side, and a number of people in this room here who are teaching those classes and advancing that knowledge. I think that provides an important foundation, as Aditi mentioned, to help understand and the ways that the physical modeling is often approached. The information content in the observations, because that's, I guess, a key part that I see for students as they start to, all these new data sets come in. Some of them are, are very informative, and others are, there's a lot of uncertainty about that, and really being able to bridge all of those data sets together requires some kind of an understanding of I guess I would say information theory is a good thing to be thinking about.
Okay, thank you. I guess like from the industry side, if someone were to, start, maybe we'll start with Caleb. Yeah, well, are there any barriers? You have an AI researcher coming in and now you want them to sort of work on these problems which have different objectives. Yeah.
I don't know if I have anything kind of helpful to say about that. Like I said before, all of the projects I work on are interdisciplinary in nature. So just communicating with who you're working with. But one thing for the students, as a student, that I've found very helpful was to attend conferences in the domain that I was working on. So I was doing land cover mapping, and I went to a GIS conference, and just kind of listening to how the GIS experts, remote sensing experts, were thinking about the land cover mapping problem really opened my eyes to some things that I could do to improve my own research on the topic. For example, they really cared a lot about shadows and how shadows might bias the results. I wasn't taking shadows into account at all. So that's something that I was able to kind of integrate into my work. And if you don't have a conference to go to, just go to like seminar series around the university. That's also very helpful too.
Okay, nice, thank you. Yeah, I guess like now there are more AI for social good workshops which happen at core AI conferences and vision conferences too, like you mentioned. That's a good place to start. Did Matt, did you have anything to add to that?
You know, I trained as an electrical engineer, and I remember thinking to myself, I don't need to program. Like it was like I don't need to learn how to do software. And looking back at that, that was pretty naive. Like software is everywhere. Like you need everybody uses Python for whatever problem you're working on. Across all sorts of disciplines. And I think AI and ML is sort of like that now. Like it's just going to be ubiquitous. It's going to we had a fairly disruptive, to some of us, reorganization at Meta recently, where we realized that AI is really, it's silly to have a centralized AI org, right? AI runs across all of our products everywhere. So I think I'd encourage students to like I was back then, like scared of writing software. I wouldn't shy away from learning the basics of machine learning of AI. Like I'll give a call out to our PyTorch. There's just amazing tutorials for how to start running PyTorch. Because going forward, it's just going to be everywhere. You're going to, and the people who are going to have the biggest impact are those who bring domain knowledge and can apply ML to that domain. I think so. That's my advice.
Okay, thank you.
The one other way that I think about it is for students or people entering the workforce is to start with that foundation. You need a foundation, and maybe I would say working forwards from your science and then working backwards from the problem you're trying to solve helps illuminate what language you need to speak. Are you trying to influence economists or policymakers or toxicologists or business people? And that's the interdisciplinary part for me, is you've got to have a core strong foundation. And then you also need to learn these languages that you were trying to influence. Who are you trying to influence, and how are you what problem are you trying to solve? And that requires either collaborating or learning those languages, whatever they are, whether it's economics or Python.
That's good to know. Thank you. We'll move on to our last question. So there's this feeling of hopelessness every time people talk about climate change. No matter how much we try, all the news we read is sort of bad. How do you stay optimistic and continue working in this space when this is how it feels? Yeah. We'll start with you, Matt, since you have the mic. Yeah.
Great. Hopelessness. Yeah, I mean, they're bad things, right? Like we pump too much CO2 into the atmosphere, like our species is messed up. And there are very vulnerable populations who are going to bear the brunt of that, and we have to make sure we address that. On the other hand, I actually see some promise. I feel like we've bent the curve in terms of starting to address this. I love all the commitments out there from the big companies, from the governments. I think there are they're optimistic, but still very plausible pathways to getting to where we need to be by 2050. So it's achievable. We can do it if we start working on it. So, and beyond that, I just I love this generation of people graduating right now. I think you're aware of the problem. You have a desire to fix it. There's actually, and there's lots of different ways to plug in right now. If you want to go the startup route, there's a ton of money behind startups in the climate space, so you can go that route. There's just a ton of work to do. So I'm pretty optimistic, actually.
Okay. What about you, Aditi? Yeah.
Yeah, definitely. I can definitely say I'm optimistic seeing a lot of the student energy, a lot of people who are really aware of the problem and want to tackle it and are looking at feasible research paths to do that. So I know there's a lot of challenges, a lot of problems going on right now, but I think the new generation is really going to be crucial to tackling these problems. And I think a lot of people are aware of that, and I think we can get there in over the next years and decades or so.
Okay, nice. That's good to know. And Dara, did you have anything to add? Do you also feel optimistic? And
Okay, so this past week doesn't make me optimistic. I got to tell you, the Supreme Court, next up is West Virginia versus EPA. They're going to rule against the ability of the US government to regulate carbon. They're going to overturn the Clean Power Plan. And the last couple of years, our Congress, our courts have been pretty not positive, I would say. We're not going in the right direction. But I think I'm in an incredibly privileged position as a professor at Berkeley and getting to engage these companies and students. We are in a very privileged position. We get to take on the hardest problem in the world, the most important problem in the world, climate change. And so there really is no time for hopelessness. It really is about, we have to look honestly at our current condition, the current situation, and take it on. I think we're about to make some decisions about how much suffering we are going to allow to which populations around the world. The climate crisis is going to result in suffering, and our choice is how we respond to those discontinuous disruptive events. Now, key to all of that is faster learning. We have to learn faster and learn faster in discontinuous events. AI is clearly going to be part of that. We have to learn faster. We have to use science and AI to take on these problems and to try to turn around this trajectory we're on.
Yeah, I agree that there is no time to be hopeless. I think I agree with that. Yeah, part of my research is like applying vision for like wildlife conservation. So what keeps me going is seeing like small success stories, however small they are. So, do you have any such success stories that you sort of like hold on to, I guess, and that's what keeps you optimistic? And yeah, Dan.
Yeah, I do. Yeah, thanks for bringing that up. So when I came to the Bay Area in 2008, I did a little bit of work with the California Public Utilities Commission on their something called the Renewable Portfolio Standard, which was the idea was to that the portfolio of power generation would be greener and cleaner in 2020 and 2030. There were some targets of 20%, 30%. And at that time, that was just total pie in the sky. We were talking about it. It was a mandate, but there was really no feasible path, no reasonable way that we could get there. And we've blown past that, those marks easily here in California with the with new technology and the will to do it. And so, yeah, I mean, that sort of gets me often thinking about this movie Finding Nemo, which I guess I watched because I have kids a lot. So, and all the fish are caught in a net and they're all swimming around and they're all scared and there's no way to get out of this thing. Then Nemo's like, okay, everybody calm down. Let's all swim in the same direction and it's not a big deal. They get out of the net. So something like that.
I love that analogy. Yeah,
that was brilliant. I guess for me, it's just the number of open problems keeps me enthusiastic and hopeful. I think it'd be very different if these things were all solved and we were just sitting here with kind of nothing to work on. But as we've seen, there's plenty to work on, and just being able to see the awesome work that everyone is doing is very encouraging. So I definitely don't feel hopeless at all.
Yeah, and I guess that's what's drawing more people to work in the space, which is also good. More people solving the problem, for sure. Are there any questions from the audience at this point before we wrap up quickly? Yes. Oh, okay.
Thank you. Thank you so much. My name is Atish Abi from the World Bank, and really it was a pleasure to listen to everyone. I just wanted to pose a very small scenario. So we typically work in areas that are highly vulnerable to the impacts of climate change. And one of the things that I haven't really heard so far is on that side of the situation. So we're talking about climate mitigation, reduction of CO2, et cetera. But in terms of the impacts of climate change on vulnerable populations, now the problem becomes tougher because these are also areas that are data deficient, imagery deficient, and probably most in the need of solutions that you guys are all working on. And one thing that we see, and we've done a little bit of work with Ritvik in the past, is that a lot of solutions are applicable in a lot of places. So things in South Asia can be applied in Africa and vice versa. So you have a lot of critical mass that can actually get. Are there areas of potential either collaboration or things that you might be working on currently that focus a little bit on this aspect related to resilience, adaptation, and just dealing with the impacts of climate change better as we go along, especially for areas that are deficient in a lot of the inputs that you might require for your ML models? Thank you.
Yeah, did anyone particularly want to like take that question? Okay, yeah.
So I'd encourage you, I don't know if you've ever seen our Data for Good effort at Meta. There's a nice web page on Data for Good. There's a ton of different data sets of that might be relevant to what you're talking about. An example of something we've done, I mentioned population density. We've also looked at population movement, income distribution, all this data from a combination of satellite data and the data that we have through our social networks. So so I think yeah, love to have you take a look at that. If there's something, if there's an idea for a new data set that you think would be impactful, that's a conversation that would be great to have.
I mean, the person I'd send you to talk to is Saul Shuang. I don't know whether you've talked to him before, but that is his whole, that's a lot of his research area, and Sherry is his postdoc, but much of his research follows climate-induced migration, and it follows these populations based on very little, you know, sparse satellite data, that kind of thing. So I would certainly go and look at his work and talk to him and his postdocs like Sherry.
I'll add to that a bit, and especially because Atishay and I have worked together quite a lot, especially in the world of resilience. Like, resilience means different things to different societies, and like there's so much societal context when we're talking about social good and climate change that we just sometimes forget about it, that we are thinking about all these problems from our point of view. Like here at Berkeley, we all live in a very nice privileged bubble. We're not a threat of our home being washed away by climate change, right? We're all going to enjoy, maybe your house are going to burn down, but separate issue. But when we talk about these data sets and we talk about these benchmarks, we really need to engage these local communities and have their context label the data, build the models. And one of our hopes and aspirations here at the BCI is not just to like sit up here in our ivory tower at Berkeley and do all this research that impacts the world at large, but it's to actually help collaborate with these other universities in Africa and other regions to actually bring their viewpoint also to the world stage, right? We hold this sort of power at Berkeley AI Research as being the leading AI institute. We want to shine a light on the plight and the viewpoints of some of these other research institutions and really bring their advancements and their progress to light. So yeah, when we talk about resilience, there's so much context that needs to go into that I think it's just an entirely fascinating world of HCI AI researches as well.
We have one more question.
Thanks. I'm Carl Bediger. I'm in the environmental science department here. But my question is really, I loved the discussion that we just had and about the interdisciplinarity. I'm curious if the panel might speak to the role of social science in that interdisciplinary picture. I heard, you know, the domain expertise and the AI expertise a lot, but as we just highlighted, there are kind of many other elements that go into making these problems really translate to outcomes on the ground, from economists like Saul or to other social science understanding the politics and the ethics involved. If
Do
anyone
you
wants
also want to
react
direct your question, or is it?
Yeah, just react to the need for social science or ethical questions.
Going to pass the mic to Caleb. Can you pass it down?
Sure. So, like a lot of these problems are people problems, and in the geospatial kind of machine learning space too, we see a lot of biases in what labeled data sources are available, and kind of to combine these two questions together. One project that we just did with the World Bank was building mapping in Oman. And we found that a lot of the publicly available building mapping models didn't work in Oman just because there's no data there. So the kind of approach we took to this was to ask the question, how few labels do we need to collect from Oman in order to actually get a model that works there? So I think engaging specifically with the communities for which the models that we build are going to be impacting is important. And then measuring how the models that we make differ in performance over different groups is also important. So releasing a building mapping model and then having it not work for the places that need it most is a big deal. And we definitely need more research in that direction.
We'll pass it.
Yeah, and I guess I just wanted to second the need for social sciences in the study of hydrology is without question in my opinion, because water resources touch on a wide range of aspects. There's a scientific component and industry, agriculture, and populations, especially vulnerable ones. Case in point, with respect to the Colorado River, we're reaching historic lows, and the century-old compact is showing its age, and showing its age in ways that some of which are really quite apparent, and will need to be renegotiated. And so there's a role for science and a role for machine learning in that, but in terms of how those renegotiations happen and how water gets apportioned fairly and equitably is something where an interdisciplinary research with social science is invaluable.
Or Aditi or Dara, did y'all have anything to add to it?
Sure. Yeah, I think one thing, definitely the role of the social sciences is that a lot of the problems that we see now that we're trying to mitigate now are in very different parts of the world. And this is absolutely affecting the populations in those parts of the world. And so I think a lot of these ideas are not necessarily transferable, because the way things are in one country or one region of a country is going to be very different. It's going to affect the population very differently in another region. And so I think it would be really important to have efforts to actually understand which population is being affected. How does that play with some of the social concepts there? I think some of the work in developmental economics is quite interesting in this regard. One person I can think of is Arun Chandrasekhar, a professor at Stanford, who he goes out to rural India, to places in Karnataka, and actually looks and talks to the population and actually sees how are things being affected there, how can we mitigate climate patterns for this particular area. And that's not necessarily transferable to completely different parts of the country or the world.
That's very interesting.
You want the microphone?
Great. So one last thing to add as well. I don't know if you see on Zoom, but there's also a professor from Pitt, Emily Wander. It's my alma mater, Hail to Pitt. She's an anthropologist and she's focused on issues like this. So if you want to work on problems like we just discussed, reach out to Emily. I'm actually very excited to talk to her later today or tomorrow, I think, to work on some of these issues as well. Unfortunately, we are out of time. So can we get a hand for all of our fantastic panelists and Medani? And thank you, Medani, for moderating so well. Thank you. It's our first time moderating. I think she did an excellent job. Of course, and none of this, I mean, Colorado's not here. He really should be here, but unfortunately COVID bit both of us here. But none of this would be possible without Colorado. It means, you know, all three of us got together a while ago now, and
Thanks, Rithvik. Thanks, everybody.
and whenever there's a front page publication for the fate of snow, you'll see Colorado's face just plastered across the front page as well. So we have now basically a time to basically hang out and get to know each other, work and talk about some interesting problems. We also have all the booze you could want and some food. So why don't we get some food, get some drinks and talk? Let's meet each other. Thank you. Well, as much as you can.